This podcast is presented by NXAI, your partner for time series foundation models and physical AI.
Hi there, welcome to a new episode of the Industrial AI Podcast. My name is Peter Seberg and I'm your host. And today I'm going to be talking to Levente Zolyomi. I hope I pronounced that correctly. We'll hear in a moment. Levente is a PhD researcher at NXAI. And he and I today are going to be talking about TiRex-2, more specifically about generalizing TiRex to multivariate data and streaming. Hi, Levente.
Hello, Peter. Nice to be here. Happy to talk about these topics. Exactly.
Yeah, nice for me as well, knowing that you are the specialist on exactly that very topic. Let's start, Levente, by you introducing yourself to our listeners, please.
Yes, of course. So, as you said, I am a PhD researcher at NXAI, and I'm also doing my PhD at the Johannes Kepler University here in Linz, Austria, under Professor Sepp Hochreiter. We have this nice time series research group that I'm a part of, and then, together with many of my other brilliant PhD colleagues, we were working on TiRex-2, and I started my PhD about a year or so ago here in Linz, and I'm also been at NXAI for about the same time as well.
Okay, we may be talking about that at the very end, but how long does a PhD take typically, or how long is it going to take further until you're going to be ready, finished?
That depends on, of course, a lot of circumstances. Usually between 3 to 5 years is the standard here.
Very good. One more, maybe more personal question. Where does your name come from? Has it got to do anything with the wind or not?
It does not have to do anything with the wind.
You know why I asked that? Because I was thinking Levante, I think is a word, a name of a specific wind coming, I don't know, coming from where. So if not, then where does it come from? Where does the name originate from?
So I grew up in Hungary, and this is actually a very traditional Hungarian name,
Wow.
Levente. So it has nothing to do with the wind. It's just a very...
Okay.
It is a coincidence, and there is only one letter difference between the spelling of my name and the wind.
Okay, you know the one of the wind.
So yeah, it is quite common.
Very good. Let's start with TiRex-2. Please give us a very quick overview, introduction, and then we'll move into the separate details of what TiRex-2 is.
Yes, of course, more than happy to. So TiRex-2 is, of course, the successor of the original TiRex model, also developed by NXAI and the JKU. And the main pitch for TiRex-2 is that it's still a time series foundation model. It is still in this zero-shot forecasting regime, but now the main improvement is that it can now handle multivariate data. It can now handle these covariates that are actually abundant everywhere in industrial applications, but are a lot more complicated to process than just a single signal. And that was the main idea behind TiRex-2, is to expand to this multivariate regime. And also in the meantime, we actually built quite a few nice improvements on top of this already existing strong base of TiRex-1. That's the high-level overview.
Very good overview. You gave me about 4 or 5 keywords that I'm just going to be asking you about. We're going to be stepping back a little bit so we all have the same baseline, and we'll take it from there. So first question is, TiRex-2, right, is the follow-up of TiRex. So tell us, what was TiRex? What is still today TiRex? And maybe, as we were talking, like age, how long does TiRex exist?
Yes, of course. Let's go into that then. So TiRex, the original TiRex model, was released in 2025 around May. And this was one of the first time series foundation models, and especially one of the first ones that moved away from this transformer architecture that's so prevalent in everywhere. And later on, we can get into the detail. Why is it so nice that we are using something more efficient than a transformer, but in a nutshell?
Right. And maybe we talk, or is that now, if, as we're talking a little bit to the past, but I'll come to it in a minute anyway. Second question then is time series foundation model. Those are two important things, again, that the majority of the listeners will know about, but remind us, what are time series data? What are time series data used for? And what are some different use cases? I mean, of course, we're talking here, we are the Industrial AI podcast. I assume that that is one use case, right? But there's completely other use cases as well. So maybe you talk a little bit about 2, 3 specific areas.
Yes, of course. So time series data is, of course, in many places. In fact, I would say more places than most people would realize. Of course, industry is one. To give maybe a bit more specific examples is, for example, in manufacturing or in any sort of machinery that has sensors that collects data like the voltage, the rotation speed of a machine, or the position or anything like this, and they collect it over time. This is a time series data inherently, and then you can of course then forecast this time series. But then other examples, for example, in the supply chain domain, you can try to forecast the demand for certain items for shipping, or the traffic flow when you come to like more industrial, or sorry, like infrastructure settings, or admission rates to hospitals. And also the entire financial industry is revolving around time series with the stock prices, the option pricing, and all of these are just many examples of time series.
Okay, sounds great. Yeah, and I personally have been involved within the industrial space with time series specifically. And we're going to come to that later as well, asking you from my experience and the algorithms that I was using at that time. 2, 3 more words, just that there's so much information on what a TiRex-2 is. Share with us the foundation model. Everybody, talking foundation models, and maybe if we have been talking foundation models since, I guess, 2-3 years, then they were typically related to maybe, let's say, words, but you're going to correct that. But now they're related to time series. So what is a foundation model, and what specifically is a foundation model when we talk about time series?
Yes, you are very much correct in that. Instead of words, I would say language, but then foundation model is definitely originated from the language domain, with this whole GPT and ChatGPT series is what kind of kicked off this line of research. And then applying this concept of having a foundational model that's really understanding a lot, like truly a foundations of a specific domain. In the case of language models, of course, language in general. And then when you apply this concept now to time series, the model that you want to get out is some time series foundation model that you can throw any data into, any sort of time series that you have collected and you want to forecast it. And then it will be able to just extract the patterns during the forecasting phase already, and you don't need to, again, train it like you would do previously before time series foundation models were taking off. You would have to train a unique model for every time series. You have to be able to forecast it well. Now we have these generic foundation models that can understand time series in general.
Now, with language, and as you said, starting with OpenAI, I guess 3-4 years ago, they and many other companies scraped the internet, kind of used close to all available language, as you said, that was available to us. Is that then similar? I mean, does foundation imply that at least you have a huge amount of? So in this case, if you say time series foundation, it implies that you have gathered a huge amount. I'm not sure if there's a minimum by which you can say it's a foundation model.
Yes, that is very much a good analogy that for language foundation models, you really had to scrape this web scale data of billions or trillions of words and tokens sometimes. For time series, I would say it is a similar setting with one extra caveat that I'm gonna get to in a second. But yes, we do have a large collection of time series, a couple 10 millions, 10, 20 millions of time series that we use during pre-training. But the unique property of time series compared to language is that you can generate completely synthetic or artificial time series yourself, where you have full control on what kind of time series you want to generate and how. And this is also now very much an active research area in this field on how do you generate this data, what you should put in it, because then you, practically speaking, can have infinite amounts of data, which is definitely not the case in language. So we do have large scale data extended with these synthetic data sets.
Okay, good. Interesting. Yeah. Yeah. Synthetic data has been around for, not sure, maybe also a couple of years. At least for me, I know that I've been trying to get my brain around it for a long, long time. And I did not always understand it. I think there was a very good case when we were talking about autonomous driving. And somebody was suggesting, yeah, you don't want to have the, and then typically maybe it's the corner cases, and the corner case maybe of where a child runs across the street and you have to brake, and so you don't want to test the data. You would rather not make that choice. So maybe you're going to do a simulation and have a child running. That, for me, that was a use case that I understood very well. I don't want to go into much detail here, but it's my question always is like, if we produce synthetic data, I mean, it's almost like turning the world upside down. How can we produce data of, it doesn't matter, medical, financial, industrial, whatever, and still make sure that they are representing our world? Because in the end, if you're going to be doing inference, then that's real world data, right? So I'm not sure how that works.
Yeah, I am completely with you on that. That the first time I heard that there is even research on fully synthetically pre-trained time series models that are also, I would say, quite good performance. Definitely better than what I would expect to something that has not seen any real world time series. But without going too much in depth of the technicalities, in general, time series and time series forecasting, you just need to understand what patterns appear in your data, at what frequencies they appear. Do they repeat? Do they maybe change? Like first you have a large peak, and then you have like a smaller peak because it was the weekend or something like that. And you also have trends. Maybe something is going up continuously, going down continuously, or it's changing trend. And if you design your synthetic data to have these properties there nicely, all we have to do is just train the model to extract these and being able to recognize them. And later on, when it sees some real world data at inference time, then it will just be able to recognize like, oh, I've actually seen this, like it's just a pattern repetition. Now I just have to copy it. And basically that's the high level overview.
Okay. Very good. And then I have two, three more. It's so, what we're talking about for me is so full of abundance of information, so to say, and words that we use all the time. And again, I just want to make sure that the majority of the listeners, I'm sorry for those of you that already know all of it, but I just want to make sure that all of us are going to be at the same level. Because then exactly what you do, and the next word is the zero shot. And the zero shot means that if I am going to take your algorithm and different from what I would be doing, like 10 years ago when I was involved more on the side, but nevertheless, we would have to train. So we would have to show our algorithm at that time, the data that we had, and we would have to train the model in front of us with our data. Now, zero shot means that I can just take TiRex-2, and I think you said also TiRex-1 already was a zero shot, and immediately it will have the capability of extending, of looking into the future of where my data is moving to. Is that correct?
Yes, largely that's the idea. Zero shot in general is a term used in many places of machine learning, Now, for time series foundation models, what we mean when we say zero shot is that the specific data that you want to forecast, most likely the model has not seen that. Later on, we can go a bit more in depth, perhaps, about benchmarking these. But in benchmarks, it's also a big step when you do zero shot. That means the model has not seen any of the benchmark data that you want to forecast on. And in industry as well, it's a very important capability, because most likely, if a company wants to use this, their proprietary data from their proprietary sensors is most likely something that we did not have access to during training, so we did not train it on. So we really have to make sure that this TiRex model can generalize to these unseen settings, making it effectively a zero-shot setting. And yes, you were also correct that the original TiRex was also operating in this zero-shot regime.
Yeah, right. Okay. So is the zero shot, is that the standard operating mode? Can I at all? So as I said, I'm gonna have, maybe let's not forget, in the end, I want to understand how to get access to the TiRex-2, but let's assume I then, as a customer, have TiRex-2, and I'm going to start exactly with that zero shot. So I'm going to connect it to my sensors, giving it the data. We're going to talk about univariate, multivariate in a moment. And then it will be, showing me where my sensors, where my data is moving. The question is, does it make sense to also, if I have, let's say, 1 month or whatever, a couple of hours, depending if it's milliseconds or days, whatever, is it possible? Does it make sense to also train it on my data? Or is it typical that it always works by the zero shot?
That's a very, very good question. And of course, it depends a lot. But in general, I would say it does make sense to have some sort of fine tuning, because for these foundation models, of course, we want to make it super general. And the same way that a language model is made to be general, for time series models as well, if you already know that maybe you don't want to forecast weather patterns, or you don't want to forecast sales patterns, but you really want to apply it to some machinery and sensor data, then we at NXAI, we can also help with that. We can fine tune it, and it can be further adjusted so it really focuses on the specific patterns and frequencies that you have in your data.
I think I understand that. Good. I continue with my still base questions, but we're gonna get close in the next couple of minutes to the specifics of the TiRex-2. Still, there is one that both TiRex and TiRex-2 have in common. They are both recurrent XLSTM-based foundation models. Now, XLSTM, we didn't talk, but that's the maybe you do want to spend just 1 or 2 lines on, and then in combination with telling us again what a recurrent model is.
Yes, that's also something that we are sort of very proud of here in Linz, having this XLSTM architecture fully developed here. This is just in 2 lines. It's a modernization of SAP's original LSTM idea, and this is a sequence processing backbone in high level. Now, the main difference, I would say, and I'm gonna compare these recurrent architectures to transformers, because they are the sort of the most prevailing architecture for most time series models, is the main difference is that transformer stores everything in its memory and compares everything to every other time step, basically, on a high level. In a recurrent architecture, because we already know that our time series is inherently ordered, we only want to sort of create an architecture that when it sees something, a new time series or a new time step, it just puts it into its own memory, and this memory remains constant in size. And all it has to do is just manage whether I want to store something, whether I want to forget something. But because of this recurrent nature of processing it sequentially, this means that both the storage cost and the processing costs are much, much lower and more favorable, which are then again important in certain deployment scenarios for these models.
Very good. Yeah, we may be coming back to, because I think the question of memory is a very important one. I think it's at the base of what already just you now told in relation to the time, the CPU that I need for running my model, if it's sequential or then if it's going to be quadratic. Yeah, and not forget that the M in the LSTM, the original 27, 28 years ago, Sepp and Dr. Father Jürgen here in Munich stands for memory as well. So maybe we come back to that later. Now, the first major difference, I'm not sure the first, I mean, it's sequentially, if that's a number one, you can confirm. Maybe that's also a little bit depending on what interests you, each listener, have. But where TiRex was dealing with univariate data, TiRex-2 deals with multivariate data. I believe I know what that is, but why don't you tell us the difference between univariate and multivariate?
Yes, I'm more than happy to. And I would also say that is the biggest change from the first to the second generation of TiRex. So to explain it best, I would say the original TiRex could look back on the history of the time series that you gave it, but only on itself. For TiRex-2, it can not only look back on its own history, but it can also now effectively gather information from other time series called covariates or multivariate time series, meaning that now it just has this whole new axis, this whole new dimension of data that it can have access to, and it can incorporate into its forecasts and into the entire forecasting pipeline, which is, I would say, quite a big improvement. And in many, many scenarios with multivariate and covariate data, we can also get into that later, what these scenarios are. This will be quite a big difference, I would say.
Yes, that's the follow-up to covariates. But then I'm not sure that I did actually completely understand it. I thought it was as easy as univariate is one variable and multivariate a number of variables, like as I've typically been used to. You know, maybe you would have whatever 100 signals, you would bring them down through mathematical ways, maybe to 10. But it's not as easy as that. It's not that TiRex only looks at one variable. That's not what univariate means.
No, that part you did understand correctly. So univariate means you only look at one variate at a time and you forecast only based on that history.
Very good, very good, very good. Then I did. Okay, yes, okay, yeah, then, I can only confirm that, from my little experience, I must say that when I was involved in several jobs, they would typically, in an industrial environment, be more than one. So I guess maybe many listeners are then also looking forward to be working with TiRex-2 for that reason. Now, you already extended it to, which I'm not so certain, but you will tell us that not only does TiRex-2 do multivariate forecasting, it does so with both past and future covariates. What does that mean?
Exactly. So covariates in general are just additional time series that the domain experts or someone who wants to use it knows that they are probably relevant to this target that we want to forecast. And past covariates are just basically covariates that we only have observed up until the same time point as the target. To give a brief example, we want to predict, let's say, the traffic flow of a junction. And we also have real-time data on how much it's raining at the moment near that village or something. And we know that the more it rains, then the more likely people are going to take their cars. They don't want to get drenched. So then we incorporate this covariate, and then TiRex can now look at it and incorporate it into the forecast that, okay, most likely now I will increase my forecast a bit because I know that it is raining more at the moment. On the other hand, future covariates are covariates where we also know the future values of them, which to me sounded a bit counterintuitive in the beginning. But I can give also a very brief example on when this is a perfect application case. So let's say you want to forecast your sales for your company. And in retail, it's known that before holidays, before Christmas, etc., the sales do go up. But we know when Christmas happens. This is already a set in time event, and we know it in the future, meaning that we can now give this information to TiRex as a future known covariate, and it's going to know that, okay, I know there is this event happening in the future, and leading up to this event, the sales will most likely go up, they will drive up. So I will also incorporate it in my forecast that they will increase. That's the main difference between this future known and past covariate cases.
So today, defining, well, at least the original choice of what is a potential or a covariate is still a human activity. Is that correct? I mean, are we? The point is, but you first need to be a human to understand what is Christmas, and then you're going to say, okay, Christmas, and then you say, okay, December 24th or whatever. But maybe in the future, if in a specific environment, the model is going to know all these different variables, maybe then the algorithm would come up with something, maybe by not saying by Christmas, but saying there is something I see in variable XYZ, which is in relationship to covariates with something else without knowing that it's talking about Christmas. I don't know.
Yes, that is to some extent. Yes, you do have to define as a human, the potential user of TiRex on what covariates you want to include. But the way TiRex-2 is built up, it can inherently also decide that from all those covariates that you provided it with, which ones are the ones that are actually meaningfully contributing to the forecast, and then put different amounts of emphasis on that. So it does have some capability to look at it. Of course, you can't give it 1,000 or 1,000,000 different covariates and then just let it figure it out. That is a bit unrealistic scenario. But in general, if you're not sure if this is useful or not, you can just confidently include it as well, and then let TiRex figure out if it's actually useful or not.
Yeah, I do recall exactly. I may have some years ago given this example, but it was only after a long time the domain experts on the shop floor not understanding why every now and then the quality of the layer on a table was having bubbles, whatever. It was not so. It was until they found out it had to do with somebody opening a window in the back because they were smoking, I believe, and there was so it had to do with, you could say, weather or window or whatever, which you then only by adding a new variable, it's almost like, is a person smoking or not, or is it cold, or is it cold outside, or and then suddenly you're going to see the relationship, and you're going to find out why things happen. Now, the TiRex-2 future covariates, they ensure, I understand, strict target causality. Maybe that's the final thing I want you to explain. We talked many, many times about correlation and causality. When you say that the covariates, they ensure the causality, what does that mean specifically?
Yeah, sure. That's also a good topic. So on a high level, this strict causality, especially in the future, is important because it's, of course, in time series forecasting, we cannot let any future information leak back into the past, as that will just make the target too easy for the model. It's just like, oh, I just repeat what I saw already in the future. Here, the strict causality just means that we are making sure that this future information only enters the model at the appropriate time, so there is no leakage of this unwanted future information into the target, and then causing these unwanted or spurious correlations that we see many, many times in many different data domains.
That's the word of the famous book, right? Spurious correlations, but that's a different topic. It's a great book that shows all these spurious correlations. Yeah. Yeah. I mean, I could, but we're not going to do that. I think I could be talking for a rather long time with you on this topic of causality, because I have this feeling that there's this huge potential in you claiming, and I'm sure if you claim that, I just take it as it is, and what that means. But we're not going to do that, because we do want to get closer to TiRex-2 here. So now, as we talk about, I have understood the univariate, multivariate, I think there are already today a number of multivariate foundation models in the market, right? And I assume that you are comparing yourself with those, and maybe you want to without, making kind of positive statements or whatever. But there is other models in the market, and towards the end or from now on, we're going to be looking at, how is TiRex-2 doing in relation to these. So maybe you can share some base numbers there with us.
Yes, truly. And yes, you are definitely right. I'd say a couple of years ago, when this first time series foundation model area kicked off, everything was univariate. Multivariate is definitely a step above, and it's a lot more of a challenging problem to solve. But now there are, of course, others. So probably the most well-known one is from Amazon, this Kronos 2 model. This is a fully transformer-based model that does not have this fully causal structure, and that's probably one of the main differences. And the other main difference is that we haven't really talked about parameter counts for these models explicitly. So I just want to mention it briefly, that the Kronos 2 model.
Yeah, just tell us what are the parameters and what is the value of maybe the end user, the listener, who's going to decide to go for one or the other solution. Also, then knowing the number of parameters.
Yes, surely. So then, probably then this other difference lies in the parameter count, and then in connection to this also how efficient can these models be under separate deployment scenarios. So this parameter count is just the number of individual parameters the model has to learn, and these all have to be stored on the device and loaded into a fast memory during the inference time. Meaning the lower your parameter count is, then the more restrictive hardware you can run the model on, and also the quicker you can get your forecast out, which if you deploy it in a scenario where you have data coming in every second is very important. So for TiRex, the multivariate model of TiRex-2 is 82 million parameters, and Kronos 2 has 120 million. So there is, I would say, an advantage of TiRex-2. But what's also something unique is if somebody decides that they do not need the multivariate capabilities of TiRex, you can turn off those sets of parameters, and then this just gets reduced to 38 million, which is then a lot smaller and enables us a lot more efficient.
Okay, now something that I just learned, maybe I just never realized. Maybe I thought that when you train these models, which can take weeks or months, right, depending on what kind of CPU you have available, and you gave us the example of the 120 million Kronos 2, 82 or 38 million for TiRex-2 multivariate or single variate. You say so the model in the end is or contains all these parameters, and you load them where? You load them in what? In memory, in CPU memory, or at time of inference, I mean?
Yeah, that kind of depends on the application scenario, of course. In the case of TiRex, we see that many of the applications of TiRex 1 were on edge devices, which have very limited compute capability. So then you would try to load it into RAM or just some fast memory access. Of course, if you have a GPU available and you want to do inference on that, then these parameters would then live in the memory of the GPU and be loaded there.
Okay, typically, yeah. Right. I don't know what is the number that we need to think of then. I mean, so for each parameter you take whatever point something megabytes. So let's say for an average of 100 million parameters, you need what kind of? Are we talking gigabytes? Are we talking terabytes? Or
I would say these are relatively still small scale, and then with some clever engineering tricks, you can shrink this down to, I would say, under 100 megabytes for something like TiRex, at least. Where I'm bringing up TiRex, of course, because we know a bit more on how it behaves under these circumstances. But I'm sure these tricks would also work on generally any model. So it's not that huge compared to something like language models where you have hundreds of gigabytes or terabytes of data just in the model parameters.
very good. So when maybe a little bit later you're going to be sharing some specific numbers. We were now comparing kind of features or capabilities, I think. So, and understand if for the moment stay at this Kronos 2, if that's what you want to see yourself compared to, understand they're both multivariate. They both to the past co-convariate, also the future covariates. What about streaming?
Yes, that's also a very good point. So streaming is in a high level. If this is also something that's, I think, easiest to visualize with an example from industry. Let's say we are collecting data from our sensors, and this sensor is measuring the rotation speed of a machine. But this rotation speed changes every second. We get new data every second, and we want to then continuously forecast. What we can do with TiRex-2 and this recurrent architecture and this fully causal structure that we built is we process the history that we have so far, and we do our forecasting. And then whenever we have now a new observation come in, like now we know, again, 1 second of data or 5 seconds of data, we can just do a single quick step of, okay, now we put this new information into our fixed memory enabled by this recurrent architecture, and we just do another forecast. Meanwhile, on something like Kronos 2 or any other transformer-based model in general that is not fully causal, you would have to recompute a lot more of the past, and sometimes your whole past, again, just because you added a tiny bit more information. This is also something that's heavily can influence the inference speed and how quick you can get your forecast in these continuous scenarios.
Because that would again be the quadratic, as you said before, rather than the sequential.
Exactly, it's quadratic, and also just generally you have to then recompute everything again and again. We don't have to recompute things that we already did. We just add things, and then we tested it to quite a long horizon, this streaming capability, and it remains stable to quite a large extrapolation length.
Now, is there any limitation? You gave the example of getting new value for single multivariate variables on a second level. Many times within the industry, we have, a millisecond deterministic values coming in. Is there a limitation from the TiRex-2 algorithmic perspective, or is that a limitation that sits more in the architecture of, CPU, GPU, access to memory, etc.?
You mean like for when it comes to the
of going below second? So if you gave the example of every second I get a new value, and then you say you can every now and then you do the calculation, so you have the capability of the streaming. Can that streaming go down also on a millisecond level, so I get 1,000 values per second?
Of course, yes. Okay, now I understand. Of course, there will be hardware limitations as well. If you have data every new millisecond, I would say at that point, just purely loading it into the memory and then doing this single step might already take longer than a millisecond. So you can't do this update. But you can go, I think, quite a lot down with this.
Okay, and one more I'm going to be asking you, as I said before, I think the importance of memory, we're already talking. So what about, I think, TiRex-2, I understand uses or has a constant memory. What does that mean exactly? And what is maybe then the advantage of that in relation to, in this case, again, Kronos 2?
I can certainly get into that. So this constant memory is specific to these recurrent architectures compared to transformers. And of course, then TiRex is, in this case, representing these recurrent architectures. Kronos 2 would represent transformer architectures in general. So what transformers do is every time you get a new data point, it does some computation on it, but it stores that data point in the memory. And whenever some future value comes in, it will then compare to that data point again. But then as you add more and more data points, you have more and more things to compare to, which then grows quadratically quite rapidly. Whereas in this constant memory setup, you basically have a fixed size of memory. You can imagine this as a vector or a matrix mathematically. But the key idea is that you only have this fixed amount of storage, and the model just learns to decide, okay, what do I need to store? What is it that I don't need to store at this point? But this also means that we are fixing the state size of the memory in the beginning, and it cannot grow further than that. Even if you were to compute for 1,000,000 time steps, you will have the exact same megabytes of memory occupied on your system if you compare just to 10 time steps, whereas with a transformer, this will grow very, very quickly into something that's not really manageable unless you have a high-grade hardware.
Okay, now share some, I don't know how you want to do it, some numbers. I mean, well, number one, I think that was already the case with TiRex, is exactly this relationship or this difference between the sequential transformer, quadratic. So it's more energy, more CPU, more memory. We know that, and that is the same, that relationship with TiRex-2 in relationship those solutions based on transformer, like understanding Kronos 2. Do you have any other specific? Is there any other specific numbers? Maybe just supporting just what it is that we just talked about. So there's many. I assume many. Or I know, I don't know them, but I know there's many different benchmarks. As always, is there one or two benchmarks you say those are the ones that you and the other providers of the time series foundation models are looking at, and our listeners are looking at, and for which reason are they looking at A or B, and where is TiRex-2 in relationship maybe to competitive models?
Yes, I can definitely address that as well. So when it comes to these benchmarks for time series foundation models, the overarching goals for them is to test on a wide range of different domains and different settings, so we can really see which time series models are truly generalizing. In this regard, I would say there are two that we can bring up here. One is Gift Eval, which has been around now for a while, and where TiRex-1 also ranked at the time of its release, and to this day actually quite much on top of the leaderboard. Here, we do not fully test for these future known covariates cases, or this doesn't test so heavily on the covariate side of things, but for example, it tests for a longer context, or it tests for a very generic ability to forecast in very different domains. And then this other one is FEFbench, which is then much more geared towards having these covariates, these past-only covariates, these future-known covariate cases, these multivariate cases. And I can say that in both of these, TiRex-2 is ranking very much on top with the best state-of-the-art models, with these time series foundation models that are often quite a bit larger in parameter count. I'm talking hundreds of millions, or now we are also seeing billions of parameters, and we are very much competing with those models at a much, much smaller scale. As I said, 80 million parameters, that what we are operating with.
Okay, so what would you suggest listeners, decision makers that are interested, that are evaluating, that are not yet inside of these benchmarks? So should they be looking specifically? The majority of the listeners will be in an industrial setting. And if it's an industrial setting, and we have typically, I would think, multivariate, but who knows, maybe some of you do look at or are interested in looking still. Is then one or the other benchmark the more specific one, while as if you are going to be talking to people in the financial market, maybe seasonality, retail, another benchmark would be more relevant for them?
So I would say in general, because one of the largest improvement of TiRex-2 is this multivariate and covariate support, and FEFbench is very much designed to do this. Looking at that will, I would say, give you a better impression on how well we are doing when it comes to these covariate cases, these future known covariate cases, especially that only FEFbench tests for. So that, I would say, is a good place to start in general. And of course, trying it out on your own data is also usually a very nice way to get a good feel on how it actually does behave.
Okay, that's a good point. Now, how does that work? Let's say more importantly, one of our listeners says, yeah, that's exactly what I would like to do. Can I test? Can I get an evaluation version? Can I get my data to you, or do you provide me with a TiRex-2 and I can test it myself, and then I compare it to whatever other may be possibly interesting for me as well? How would that work?
Yeah, so much like the original TiRex model, where it was available fully openly on Hugging Face, TiRex-2 is also available with very similar licensing terms, very similar terms, but the main goal for us is so that everyone can try it out and everyone can see what it can do. And of course, for any sort of, like, if you then like it, or if you think that maybe we can make it somehow even better for your use case, then NXAI is definitely here to help. And then they should definitely get in contact with us, as we can definitely fine tune and customize this as well. But the base model is very much available to try out for everyone online. Very similar setup to TiRex-1.
Very good. Rounding it up, maybe, what have we just heard from you in the last? Oh, we already talked. Peter always talks for about an hour with the people that I have in my podcast. Bringing it together, what is, in 1-2 lines, what is TiRex-2 more than, other than what TiRex has been until today?
So TiRex-2 is just this next step of the previous TiRex model that can now incorporate other covariates in its forecast, can now do multivariate forecasting natively, retaining very much similar capabilities of TiRex-1 with regards to this constant memory and scaling. And there are also now this multivariate and other improvements that can now make it even more competitive in this benchmark and in this landscape in general.
Sounds great. Before we close, Levente, tell us, you mentioned you are based yourself, I believe, that's what you said, in Linz. Tell us a little bit about, maybe also assuming that you as a company are looking for talent, and what should they bring? How does your work, how does your day working on a product like TiRex-2, how does that look like? What is the kind of things that you work on, and what is maybe the type of people, talent, where you as a company do not yet have enough of?
Yes, that's that's a great question. So I am part of the research team. I am also a PhD student, so my day is very much a blend of what a PhD student would do, reading papers, catching up on new research, and then also gathering ideas. But then on the other hand, NXAI's domains, like this time series domain especially, is then heavily influencing my research then, and then trying to work on things that are then can be made into NXAI's business in general. That's what we do on the research side. And then, of course, we have very, very good engineers that can then translate these models that we develop into actual customer projects. So I would say, if you are interested in that, if you're interested in working with these time series models, or even more so getting them into real life deployment scenarios, sometimes challenging scenarios, then I would say they should definitely get in contact with us.
Okay. And typically the people around you, yourself, are people that have come from what? From mathematics, starting with SAP. I know who studied here mathematics. I happened to be at the Munich Technical University again last week for other reasons, but I thought of SAP at that time. So is that typically mathematics? And as these days, and maybe you tell us 1-2 words about how it works in Linz, is that typically then the direction of, I don't know, artificial intelligence, machine learning, or what typically would you be looking for people bringing with them if they would apply for, possibly working with you?
So the backgrounds of the people are definitely from many, many different places. But if you studied something like computer science or data science, or if you worked in the past with machine learning projects, with maybe actually hardware level optimizations even, or like a hardware engineer or something like that, that would definitely be something that fully fits in. But then, yes, as you said, also we have people from mathematics and different backgrounds as well. So it's not just fully restricted to computer science or this machine learning and this AI area of studies and expertise.
Very good. And not to forget to mention being close around one of the top researchers in this field, Zap Hochreiter, which I'm sure is wonderful to be working with. Levente, thank you very much for your time. Thank you very much sharing with us the details of TiRex-2. Thank you very much and good luck. And I would say those listeners of you that are interested, you know where to go. NXAI, maybe you can contact Levente directly or somebody else at NXAI.
Yes, more than happy to.
Levente, thank you very much.
Thanks for having me.
Bye-bye.
Bye-bye.